and 10 questions, 0.5 marks questions. So those are the 0.5 marks question. They are just like you have to remember something. That kind of things is there, which is based on just your memory based test. So it will be very easier if you are clear about the concept, you have studied it properly, then you can answer it very easily. And 5 questions will be there, which will be based on the numerical. So numerical can be formula based numerical, in your diode concept, in your diode current equation, it is involving some resistance, dynamic resistance calculation. Yes?
Numericals and the rest of them are theoretical.
Yeah, theoretical means just memory based. So just about the concept. Okay.
Ma'am, the questions will be MCQ type, na?
Yeah, MCQ type. Okay, MCQ type question. So 5 questions will be 1 mark question where you need to calculate something like that.
Okay, ma'am.
Time limit of the test?
Half an hour. Half an hour time is there.
From 6 p.m. na ma'am?
Yes, 6 to 6:30.
Okay.
And try to submit it in proper time, because after time it will not accept. So before 6:30 you have to submit.
Ma'am, please mention the time limit with the assignment.
Which assignment? Lab assignment, na?
No, with the quiz.
No, the quiz, ma'am.
Yeah, so 6 to 6:30. So time limit will be only beyond 6:30. Maximum 2 or 3 minutes will be given. After that, it will be closed. It will not accept.
Ma'am, please increase the time limit to 40 to 50 minutes.
Why? If 40 to 50 minutes we will increase, then most of the students get the answer from their friends. So that issue is there. Previous year also in online, many students that they complained that when we increase the time to 5 minutes also, then some students get benefited, and some those who submitted earlier, they are having less mark, and those who are submitting late, they get good marks. So it is not the fair things. So you should.
Ma'am, if it is a half an hour paper, we have to submit it in 25 minutes.
Not 25 minutes, just how much time it will take to submit, just to click a button. So at 6:20.
Sometimes there is a glitch in the Microsoft Teams, and Microsoft Teams does not accept the answers.
Okay.
Yes, ma'am.
So maximum 5 minutes extension we can give. Otherwise, you will be in trouble.
Kindly make it 6:35, ma'am.
Okay.
Yes, ma'am. That.
Okay.
Ma'am, when you upload the assignment of test, you just write the time limit.
Sure. It will be shown to you. It will, when we set the quiz, there setting is there, which is the due time and which is the extended time. That is, all things are mentioned there.
Ma'am, yesterday we didn't get that. That's why we are telling you so.
Oh, time limit was not given.
No, ma'am.
No, ma'am.
Okay. Which test you were having yesterday? Maths.
Maths and chemistry.
Okay,
Maths and
both,
chemistry.
Maths and chemistry both in same day.
Yes, ma'am.
Yes, ma'am.
Okay.
And ma'am, both were of 50 minutes.
50 minutes. So
Yes,
how many
ma'am, both
questions were?
test.
How many?
In
10
chemistry,
questions in maths.
Chemistry it is 20, and in maths it is 10.
Okay. Is any was subjective or all are MCQ?
Ma'am, all
MCQ.
All are MCQ. Maths are totally,
maths are obviously numerical.
but numerical based.
Okay. Okay, in EC it is usually we take half an hour, so 6 to 6:30. Okay, so let's start. So I hope you all have derived this VDC, IDC, VRMS, IRMS for this waveform. Have you derived?
Yes, ma'am.
Yeah. So
Yes, ma'am.
yeah. And just someone was asking in the previous class about the VDC, VRMS, VRRMS. So this is the one simulated output I have shown here. It is simulation. This simulation is done in MATLAB. So just to show you what is the difference between your VDC, VRMS and VRRMS. So you just see here in a half wave rectifier, if this is the output waveform. So when we calculate like peak value, BM value is 5 volt. So there it is, your VDC value comes at about 1.5 volt. So very small VDC we are getting from the half wave rectifier circuit. And this green color dotted line, it is showing the VRMS value. So VRMS means whenever we are calculating the RMS of this waveform, okay, and VRMS is the your value which is calculated for the AC content of this waveform. So here we are excluding the DC. As I have told you that in by Fourier series technique or by Fourier transform technique, usually for the periodic waveform we use the Fourier series technique. So Fourier series is the expansion of any waveform. So as per the Fourier series, any periodic waveform can be represented as one DC component and the different sinusoids, means sine, and in terms of sine and cosine, the rest part can be represented separately. So we can excluding the DC part, only considering the AC part and finding the RMS, that will be your VRMS. So this is the RMS value of this ripple. So this value is coming 3.5 volt. Okay, so 3.5 volt VRMS is there. So this is for the half wave rectifier circuit. When we compute these values for the full wave rectifier circuit, you can see that this for the same value of your BM 5 volt, we are getting a DC voltage of 3 point something. And this RMS value is 3.5 volt. And your VRMS is also 3.5 volt. So here the DC value you are getting more. So this is how in full wave rectifier circuit usually we get a better DC value in comparison to your half wave rectifier circuit. So still it is in this either it may be half wave or full wave rectifier circuit, whatever the output waveform we are getting, that is not in a pure DC form, it is a pulsating DC form. So here we can see the frequency of this is same as the frequency of your input signal, because here also the cycle is 0 to this one, this is a cycle, and also the input also the same cycle. So we can say the frequency of, if it is a sinusoidal signal, then frequency of your input is, if it is 2 pi, then frequency of output is also the frequency time period of your input and output both are 2 pi. But in case of your half wave full wave rectifier circuit, if the time period of the input is 2 pi, the time period of your output is pi. So obviously the frequency of your output will increase. Okay, frequency of the output signal is twice that of your input signal in case of your full wave rectifier circuit. So this concept may be used for calculating some values or some numerical. So you should just aware of that in half wave rectifier, what is the frequency of the output signal and what is the frequency of the output signal of the full wave rectifier circuit. So in the evening class I will solve some numerical from based on this rectifier also. So there is a comparison table from the book just I have taken, so you can just have a gist of this half wave rectifier and full wave rectifier circuit. So in the full wave rectifier circuit, two full wave rectifier circuits are there, center tap and bridge circuit. So there are comparison of every parameters is given, so you can follow this. Okay, so next we have to just use the filter circuit to get the pure DC signal from the AC signal. So in the lab class you have done it and you can observe also that how it is coming. Okay, so when you use the filter circuit, so in the AC component of the rectifier output, whatever it is present in the AC component of in the output waveform, pulsating DC output waveform, it can be eliminated by using a filter circuit. So usually in electronics, filter circuits filters can be different type of filter classification is also there, like your active filter, passive filter, or high pass, low pass, band pass. Different type of classifications of filters are there. Okay, so basically in this rectifier the passive filters are used. Passive filter means the filter which is designed by using passive components like your capacitor, your inductor. These are the components whatever it is used for the AC in this filtering circuit. So either you can use a filter like only the C filter or a shunt capacitor you can use. So we can have this like. So rectifier. Rectifier with filter. Okay, so it can be a C filter, it can be a L filter, it can be your CLC filter also. CLC filter. So it is also called as your pi filter. Okay, so whenever we use the capacitor in parallel to the load, it behaves like a filter. So how it behaves like a filter? So like what is the reactance of the capacitor? What is the reactance of the capacitor? This is
1 upon omega c.
Yeah, 1 upon omega c. So this is just here, it is clearly visible. Let's use this one. So suppose this is the input waveform and we have used the capacitor in series connection. So here when the output current will flow through the load, before that we just add one capacitor. So how it will behave when we add one capacitor, like capacitor is having a reactance of like Xc is equal to 1 by 2 pi Fc, or we can say it is omega c. Okay, so for the higher frequency or for the low frequency, how the capacitor is behaving? So if the frequency tends to 0, that is the low frequency we can say, because the DC is having 0 frequency, so we can consider the DC part as the low frequency component and AC part as the high frequency component. So if the frequency tends to 0, then what will be Xc? That is 1 by 0 is infinite. So this capacitor reactance is infinite. So it will be behaving like a open circuit. So the capacitor behaves like a open circuit. So in open circuit condition, directly the current will pass through the load. So just wait 1 minute. मेरा अभी तो शुरू हुआ है 11 क्या काम
एक्चुअली विशाल सर मान रहे हैं सारा क्या लिस्ट है इंस्ट्रूमेंट पे हम क्या करते हैं ना
हाँ
इंस्ट्रूमेंट के बगल में इंस्ट्रूमेंट का नाम देते हैं
अच्छा
उनको भी सहूलियत होगा सबका हम लोग को एक्स्ट्रा भी है पूरा लैब का देने के लिए पूरा लैब का देने की जरूरत ही नहीं है
हाँ
लैब का
ये जो विजयनाथ सर का कुछ आगे वही वाला है अच्छा अभी आया क्या AM किट और FM किट आ गया है तो उसका कल कब डेमो फेमो होगा उसको बुलाना होगा
अभी लाने गया
उस दिन आया था ऑफिस में कार्टून
हैंडओवर नहीं किया
अच्छा नहीं
एक कार्टून है 4 कार्टून आया था 3 कार्टून आया था
अच्छा
उसी में है
अच्छा देख लीजिएगा और उसका कब डेमोन्स्ट्रेशन के लिए आएगा उसको फिर बुलाना होगा
लैब खाली होता हूँ लैब तो सब जगह देखते हैं कहाँ से करवाना हूँ जैसे बोला पता होगा ना
कहीं पे भी करवा लेंगे नहीं तो फिर डिले हो जाता है ना तो रह जाता है जैसे लाल साहब मंगवाए थे सारा किट वैसे रखा हुआ है कुछ हुआ नहीं उसका डेमोन्स्ट्रेशन ठीक है तो क्लास खत्म होता है हम आते हैं
नहीं यहीं पर आएंगे आपके पास ही रहने दीजिए हमको फोन कर दीजिएगा
अच्छा।
ये वाला में मतलब यहाँ साइड में लिख देंगे CRO की जरूरत है जैसे निशाजन पैटर्न का है तो CRO की जरूरत है फंक्शन 2 की ठीक है सेकंड एक्सपेरिमेंट में PN जंक्शन है इसमें जरूरत नहीं है इसमें कोई इंस्ट्रूमेंट का जरूरत नहीं पड़ता है वोल्ट मीटर का जरूरत पड़ता है ठीक है उसके बाद है तीसरा जो है जीनर वाला में खाली PS लगता है पावर सप्लाई लगता है वही साइड में लिख देंगे वो दे देंगे वो अच्छा रहेगा
ठीक है और ये वाला भी ना अपडेटेड वाला रखना पड़ेगा क्योंकि वेबसाइट में दूसरा लिस्ट रखा हुआ है
निकाल लीजिएगा
ठीक ओके so capacitor behaves like open circuit so when it is open circuited directly the current will pass through the load and we are getting the output for that low frequency component. But as the frequency increases, the frequency, let's very high frequency, so we represent usually high frequency mean frequency tends to infinite, so this XC will be 1 by infinite, that is 0. So that means capacitor is having zero reactance, means we can just treat the capacitor as a short circuit equivalent. So if it is short circuit equivalent, then for higher frequency in this circuit, this capacitor will be behaving like a short circuit. So the current, if it is the short circuit, then if the current is, and it is coming from here, so the current will not go through the load, as there is a low resistance part or the zero resistance path is there in between, so the current will pass through this. So at the load we are not getting the output due to the high frequency component. So here automatically the high frequency means the AC content is blocked and DC is passed. So this is the concept where we are using the capacitor, how the DC is separated from the AC part. So usually the low frequency component gets filtered and it is obtained at the output, and high frequency components are filtered out. So if mathematically, if you want to derive this,
can you explain it just once again?
Yeah. So if the capacitor we are using in parallel connection, so as its reactance is 1 by 2 pi FC. Okay, so for the low frequency components means when we consider the DC part, so for the DC frequency tends to 0 we will represent. Okay, so if you analyze a particular signal in more detail, like in the Fourier series analysis if you do, so first term will be your DC term, the signal will be like whatever the suppose input signal it is or the output signal, if you just apply the Fourier series and that you just separate the term, or you can just have the different frequency component can be represented separately. So first component will be your DC component in the Fourier series expansion. Next will be your first fundamental frequency. Then some sinusoids or some sine term will be there where the frequency is, let's say F1, then F2. So as the we are moving by term, so from the low frequency to higher frequency, for different frequency the terms get separated. Okay, so the low frequency components can pass through the capacitor, as for the low frequency the capacitor behaves like a open circuit, because 1 by 2 pi FC the reactance will be infinite, so infinite reactance means open circuit, so directly the low frequency current can be passed through the load and we can get the output. But as the frequency is higher, its reactance becomes 0, so very low resistive path can be, or the short circuit path is created across the capacitor. So whatever the current it is passing through this circuit, instead of going to the load, it will pass through the capacitor. So the high frequency current will not move to the load and we are not getting the output for that. So the high frequency component get filtered out and only the low frequency components are low frequency component, or for the output voltage for low frequency current can be obtained. So this is the concept behind how the capacitor is used for filter. If it is the inductor, what is the reactance? It is omega L, so 2 pi F into L. So the inductor has to be connected in series connection. Whenever the inductor filter is used, actually in your syllabus only capacitor filter analysis is there. Just for your knowledge I am saying that if you are using an inductor means its reactance is omega L. Okay, so there you have to just connect series. Just hold on a minute, actually series calling. Good morning sir.
हेलो.
Yes sir.
तो मीटिंग कितने बजे का रखी हो?
सर अभी मेरा क्लास चल रहा है, क्लास खत्म होने के बाद मैं बात करके फिर रख लेती हूँ.
ठीक है, 12 के बाद ही रखना फिर.
ओके सर, ठीक है.
ठीक है.
हाँ सर.
एक जगह हम जा रहे हैं, जाके आ रहे हैं, ठीक है.
ओके सर. So when we are using the inductor as a filter, in that case the inductor has to be placed in series connection. So we can, for the low frequency, if it is the inductor, Like if it is the inductor, its reactance will be 2 pi FL. So for low frequency, F will be 0. So it will be 0 means 0 resistance path. So low frequency will be like if you are putting an inductor here. So for the low frequency, it behaves like a short circuit, and for high frequency, it behaves like a open circuit. So when inductor is connected as a filter, it is connected in series connection. When capacitor is connected as a filter, it is connected as shunt connection. And one more filter, I was telling that this is a CLC filter or the pi filter. The structure is like this. It is C, then L, then C. Means we can say the two-stage filtering we will do here. Two-stage filtering we can do here. Once it is filtered through the capacitor, then it is filtered through the inductor, then again it is filtered through the capacitor. So this is the concept behind the filtering. So which filter we are using? Earlier it was there in the lab, for all the filter analysis was there, but now in the revised syllabus only capacitor filter is there. Okay, so in capacitor filter, by using the capacitor filter, whatever we are doing, so in capacitor filter, when we use the waveform, let us observe the waveform, how the capacitor is that allowing or it is not allowing. So let us analyze in your waveform. So in waveform, we can see that actually what is the concept as little bit we have discussed in the lab. So when we use the capacitor, the fundamentally principle of your capacitor, it will store the charge. That is the property of your capacitor. So how it will store the charge? It is not getting, if you are taking a charge, some 10 volt, and according to that whatever the charge, and that is not suddenly stored in the capacitor. It takes some time to get charge to its maximum value. Gradually it will charge. So usually the capacitor there is a time constant. There is a concept called time constant. So it is for the capacitor, the time constant tau, it is represented as the resistance into capacitance through the circuit. So in the circuit, whatever the resistance is there and whatever the value of your capacitor is there, according to that the time constant is decided. Okay, so in capacitor, we can say that when in the input waveform, that means when the current is moving from 0 to maximum and maximum to again 0, 0 to again negative, like that. If you are saying that means the capacitor will charge. When it will charge? When the diode get forward biased. Means in the circuit when the diode get forward biased. So in the half wave rectifier, if you consider, so here the diode is there. So when the diode is forward biased, that means the current is passing through this circuit. So for that case, the capacitor is getting charged. So when the diode is get forward biased, from this 0 to maximum or 0 to, we can say, as it is the ideal diode we are considering for the analysis. So 0 to pi, for this cycle the diode will be in the forward biased mode. Okay, the circuit will be in the forward biased mode, or the diode will be in the forward biased mode. In that case, the diode behaves like a short circuit. Here, like earlier, the diode was there, so the diode behaves like a short circuit, and the current is passing through this capacitor. So during this instant, the capacitor gets charged. So up to from 0 to peak value, when we are applying the voltage, within this duration, the capacitor gets charged. Okay, so how much time it will take to charge? It is the resistance of the circuit into the capacitance. So the capacitor value is fixed, and resistance value means whatever the resistance of the diode in the forward bias condition, that is the very small dynamic resistance of the diode is there. So that resistance into the capacitor. So this charging time constant is very, very small time. So that's where the capacitor get charged very short, with a very short duration. Okay, so from 0 to, if you consider from 0 to this, then the capacitor will charge to this within a very short period of time. That is from this 0 to whatever, suppose the maximum value is pi by 2. So within this peak value, the capacitor gets charged and it will store its maximum charge there. And what will be the maximum voltage across the capacitor? That will be your peak value of this input waveform, that is the B max. This is the, if it is B max, then it is peak value. Up to this peak value, it will get charged. Then when the voltage starts decreasing, the capacitor will also little bit discharged, okay, because the supply voltage, here the voltage is more and here the voltage, applied voltage is decreasing. So obviously for maintaining this it will be discharge, okay, it will discharge. And up to which amount it will discharge, like suppose up to this, from this pi by 2 pi, this is discharging. Again from pi to 2 pi, when the diode get into the negative half cycle, the diode is now reverse bias condition. So in the reverse bias condition, this will be open circuited, this part will be open circuited. So when it is open circuited, the current will not pass through the capacitor. So now the capacitor is having a voltage approximately your Vm value, little bit it is discharged very little amount, and almost Vm amount of voltage is here, and here a load is also there. So this becomes a closed circuit. So the capacitor will discharge through this load. The capacitor will now discharge through the load as the current is going on. So it will discharge through the load. So for the discharging voltage, it will discharge up to how much cycle, how much part it will discharge, means whenever the diode will be in the reverse bias condition, it will discharge. Up to this period, it will discharge. Okay, so up to this, actually this time constant, suppose this is the charging and this is discharging. So discharging will be your load resistance. This is the diode forward resistance. We can say this is the RD, diode resistance into capacitance, and here it is load into capacitance. So the load resistance is usually a very higher resistance. So this discharging time is very lengthier, or it will take a higher time to discharge. So it will slowly discharge. And you have to maintain the time constant in such a way that means when it is discharging very slowly, and this duration should be you should take the time in such a way that means this, you just compare this duration like time period. It is usually the time period by half of your time period. So the duration of the pulse duration, or we can say the signal duration, this should be maintained in such a way that this duration should be very smaller or higher for this as comparison to the discharging time. So this duration should be very small in comparison to your discharging time. So it will take to discharge this amount, and after reaching to the very significant drop in the voltage, until it is going to the significant drop, again the positive half cycle start. So again when positive half cycle start, again the capacitor will charge to its peak value. Then it will be in the peak value, and again it will discharge very slowly. Okay, so very small amount of discharge will be done. Then again the next half cycle, next positive will come. So it will again for charge to its maximum value. So if you maintain this period in such a way that, like suppose this duration is very small in comparison to this discharging time, then we can get a very pure DC signal, isn't it? If you give because this input waveform whatever we are taking, okay, its frequency is upon you, how much frequency you are taking, isn't it? Can you change the frequency according to your requirement of the signal? Can you change the frequency? There is no answer. Praveen?
Ma'am, can we change the frequency using voltage regulator?
No. I am saying that when we are taking the input signal. Yeah, when we are taking the input signal, okay, we can take the signal frequency. We can take the you can generate a signal as as per your requirement. You will generate the signal, na?
Yes, ma'am.
Yes, ma'am.
Yeah. So that frequency, if you are maintaining the frequency, like if you want to minimize this duration, then what we have to do? That means we have to increase the frequency, so minimize the time period Okay, so if this period is very small, then what will happen? It is the capacitor will discharge very little amount, then again it is charged to this amount. Okay, like this. So we will get a better DC voltage there. Okay, so usually the ratio of this charging and discharging time constant is taken like this tau discharging. This discharging is usually taken that's more than equal to 5 of tau charging. This kind of usually it is taken. Okay, more than 5 tau of charging means charging time constant jitna bhi lagta hai, discharging time constant is more than 5 times it takes. If you are considering, then we can have a DC signal. Okay, so this kind of waveform we are getting in the half-wave rectifier circuit. Okay, in half-wave rectifier we are getting this kind of waveform. Okay, so now you have to, yes.
And at which point the C filter will detect DC and at which point AC component?
Means?
The frequency is very low at a DC component, and
Yes.
during AC it is very high. So at which point C filter will detect DC component and AC component?
It is actually to understand the concept, either we can have this concept like how the capacitor is behaving like a filter, means it is filtering out the AC component, and this is one analysis actually how this DC waveform is coming. How this DC waveform is coming. Okay, this is the way of analysis. Okay, here actually we are saying that capacitor is filtering out the AC component. There is not a significant point that from beyond this point it will not allow beyond beyond this and below this point it will allow, not like a very solid demarcation point is there. Okay, this is the theoretically the concept we are doing. So that is based upon the how much value of your capacitance value is there, what is the frequency of the signal, depending upon that how much resistance it is providing. That's why we are using this CLC filter. Like if it is possible that only by using a capacitor filter, if 100% the AC component can be removed and 100% DC can be separated, it is not like that. Okay. So based upon the values of the components value, how much it is providing, and what is that, also there is a feasibility. Like suppose if you want to the capacitor value very higher, okay, if you want the capacitance value very high, then only your DC is coming properly. In that case also it is not feasible, because the higher value of your capacitance means obviously it will be very bulky capacitance, very big size of capacitor, and that capacitor cannot be used in a electronic circuit, very small circuit where you are just like suppose in your charger, inside the charger if you are making the circuit, it is not possible to have a very big capacitor there. Many other components are also there. So there are several factors are there based on which you can choose the capacitance value. Like when we, in this case, when we capacitor value this value, some amount of your AC is filtered out, still some AC component will be there. So that some component of AC can be filtered out through the inductor. Then some components of your AC will be filtered through the capacitor. So the efficiency by using this CLC will be more in comparison to your L or C filter. So there are various type of analysis is there. So just only theoretical purpose to show how the capacitor is able to pass the DC, not the AC, that thing is analyzed here. But there is a not certain point that exactly at this frequency it is removing or it is allowing. Okay. So this is about the waveform, how it is getting, we're getting the waveform from the pulsating DC to approaching to the pure DC signal. Not the exactly, we're not saying that it is the 100% DC, because DC means we have to take the directly the straight line. But here also we are not getting a straight line. So the average of this will be better than the average of this DC voltage what we obtained here. Okay, so now you have to calculate the ripple factor for this waveform. Okay, so this is for the half wave rectifier circuit. Likewise, for the full wave rectifier circuit also we can analyze it in the similar way, and we can get the waveform like this. You just observe here. So in the full wave rectifier circuit, only the difference is that here we are getting the waveform which is frequency is more. So the pulsating DC, whatever we are getting, so for the pi to 2 pi also we are getting the waveform. And here the capacitor, applying the capacitor also, this type of waveform we are getting by using the capacitor. Okay, so when you practically analyze this may not be visualized as a triangular waveform. Very little variation is shown. Okay, and if you want to zoom it and you can observe the difference, then this ripple can be shown. So now you have to find the ripple factor for both the cases, for this filtered output of your full wave rectifier circuit and filtered output of your half wave rectifier circuit. So there we need to calculate. So here we will have this ripple factor. We'll get, this is for the half wave rectifier circuit, this is 1/2√3 FCRL. This is the value. Okay, this is the value. 1/2√3 FCRL. So how it is coming, the derivation is there. So I will share this, you will go through the derivation or what? I will do the derivation.
Ma'am, actually, I had a doubt in this. Ma'am, how
Yes.
do we calculate the VDC or the V average for this waveform? Why is it VL minus VR/2?
Actually, this is as this waveform is not a sinusoidal waveform, isn't it? It
Yes,
is just like a triangular waveform.
Yes, ma'am.
So when we calculate the this average for a triangular waveform,
Yes,
so how to calculate the average of triangular waveform? If it is a triangular waveform, so how to calculate the RMS value or the average value for this triangular waveform? Can you calculate? Actually, what is the basic concept for calculating the average value? What we take in the sinusoidal waveform? When we take the integration.
Area.
Okay? Yeah, and area we are calculating by integrating that. So here also you need to calculate the waveform. Like suppose, for example, just let me show you. Suppose this kind of waveform we are getting. Suppose we are calculating a triangular waveform like this. So different type of triangular waveform can be there. Like suppose this is one kind of triangular waveform. Okay, this is, so it is actually equal, it is vertical. Okay, so for this kind of triangular waveform, so how to calculate the average of this waveform? Like suppose this is 0, this is period is time period is t. Suppose this is t/2. Okay, so here suppose this is the maximum value is Vm. Okay, and suppose the slope of this point is, let's say, slope m. So what will be this point? This point coordinate will be t/2 in the x-axis and y-axis will be Vm, and for this the coordinate will be 0, 0. Okay, so if you want to, suppose this is the signal, this signal is your Vt, let's say with respect to time, the signal is your Vt. So we can say this Vt will be, it can be represented as mathematically. What will be Vt? That this is the straight line m having a slope m. So we can say this part of the waveform, that is 0 to t/2. If the time is 0 to t/2. For this case, the straight line is, what is the equation of this straight line? It will be mx, or we can say this will be m into t. Okay, and from t/2 to t, if the time period is from, this time value is from t/2 greater than t/2 to less than t. So for this period, this value is 0. Now the waveform is represented mathematically like this, like in the sinusoidal waveform. In the sinusoidal waveform, it is the sinusoidal waveform. Then we are representing it as a Vm sin omega t. In this way, we are representing this mathematical notation. So for this waveform, we are representing like this. Okay. Now the RMS value, if you want to calculate, or the average value, if you want to calculate, suppose the RMS value I need to calculate. So it will be root of 1/t, this is the average for making the average, integration 0 to t Vt square dt. Okay, so by taking this kind of waveform, so Vt is now this one, so you just check the limit, change the limit for Vt from 0 to t by 2, t by 2 to t, and apply this value. And how to calculate this slope? How to calculate the slope of a straight line? M is equal to y2 minus y1 by x2 minus x1. This one is the formula na, for calculating the slope. Y2
Yes,
minus y1 by x2 minus x1. So by taking this is Bm minus 0 by t by 2 minus 0. So we can say this will be twice Bm by t. So by putting this value and integrating this, you can find the RMS value. Likewise, you can calculate the average value. Just calculate the area, means this is integration of this Vt dt, and just take the average. So 1 by t by 2 you can take. So that will be the average of that signal. So any kind of waveform you can take. It may be this kind of waveform, or the triangular waveform can be this kind of waveform, or it can be a equal triangle also we can take. Okay, this kind of triangle also we can take. So according to that, you can calculate the average and RMS value, and once the average and RMS value you obtain, then all other parameters you can obtain. Okay, so actually if you derive all these things, then time may not permit. So I will upload this derivation pages of the book in a particular book. It is given very nicely. So I can upload this 2 pages, so you can go through it. So for the quiz purpose, actually formulas are required for the analysis or for calculation of the numerical. So for the half wave rectifier, filtered output is having a ripple factor. So the ripple factor of half wave rectifier with C filter. With C filter, this value comes around, this is R is equal to 1 by 2 root 3 FCRL. Okay, and for the full wave rectifier circuit, this ripple factor or full wave rectifier circuit with C filter will be, this value is your this is the RMS, AC RMS by VDC. So the final value will come, this is 1 by 4 root 3 into FC into RL. So these two formula, for the time being, you just remember these two formula for half wave and full wave rectifier circuit, and you can calculate the ripple factor. So I will upload the book page whatever where these derivations are given, and also I will prepare the note for this complete, and I will give you after completion of this module. So it will be helpful for you for your end semester examination. Maybe your what happen if the government will permit, then it may be like that. End semester may be your offline, so it may possibility is there also. So you should be careful about the derivation and all these things. So for the time being, you just remember the formula for this half wave rectifier and full wave rectifier with filter. What is the ripple factor? So when you calculate a particular value without filter and with filter, then the difference can be observed. Okay, without filter, the ripple factor of half wave rectifier is how much the ripple factor? 1.21. And if you apply a filter, particular filter, capacitor filter, or having certain capacitance value, and for the same load and same frequency of the input, if you calculate the ripple factor, then obviously it is the capacitance value, it is coming in the denominator. So obviously the ripple factor will reduce significantly. Okay, and if it is the full wave rectifier, again it is 4 root 3. Here it is 2 root 3. Here it is 4 root 3. So again the ripple factor is reduced significantly in the full wave rectifier circuit if you put a capacitor. So this is about the half wave and full wave rectifier circuit with filter. So in the evening class, like in the 4:30, we will take the class. So we will solve some numericals as well. We will start the Zener diode. Okay. If beyond 5:20 also we will extend 10-15 minutes, then is there any issue?
No, ma'am.
So
No, ma'am.
yeah, we will solve some numerical and we will also start the Zener diode, so that tomorrow morning class we can complete the Zener diode. Okay, and in the afternoon class, like 1:30 to 2:20, both the section will combinedly we will take the class and we will solve the numericals of Zener diode, so that you can appear the quiz. And in the 3:30 we will not take the class. You read yourself for the quiz. So tomorrow in both the class we will have 10 to 10:50 and your 1:30 to 2:20. Both the class I will take, and we will solve some numericals from Zener also. Okay.
Okay, ma'am.
So let me take the attendance. And it's a last warning. You can think as the warning also. I'm requesting whoever is doing this stupid thing, don't do these things. Okay. Don't hurt anybody.
Previous
Okay.
class slide.
Yes.
And have you uploaded previous class slides? It was not
Actually, not opening.
At my end, it was not opening.
Okay, I will upload the today's Word file, whatever we have discussed. Okay, and also 2 pages of that derivation part, whatever it is there. So I will upload that. You can go through it.
Okay, ma'am.
Can I make an announcement?
Yes.
Ma'am, there will be no class of BME. Sir is busy in some another meeting, so the class will be held in tomorrow morning.
BME. When the class is there?
The next class.
Just after this next from.
Bruh.
Okay, 11 to 11:50.
Yes, ma'am.
Okay, so we can continue. Okay, so let us continue for a few more times, so that the numerical parts, whatever the numericals are there, we can complete it.
Ma'am, you take this class, and there will be class at 4:30 today.
Yeah, 4:30 class I will take. Actually, I need to organize some meeting. So HOD has called me and he told that some meeting has to be organized at 12. So before that I need some time. So if you say, then I can solve some numerical from the rectifier part.
Excuse me,
and
ma'am.
in the yes.
Ma'am, so tomorrow. Ma'am, you have.
Yes,
Ma'am,
yes.
so tomorrow in the afternoon we'll complete the syllabus, and after 2 hours we'll give the quiz.
So what happened?
I think it's the time is less for preparation.
So afternoon you don't want class. So morning I want.
At least one day after completing the syllabus we should get.
So actually what happened yesterday, I was about to take the class, but in the same room one more teacher was taking the class. Actually we are sharing the room, so it was not possible that both we teach, so it will create the interference.
Ma'am, will the syllabus be completed by today, sir?
I will complete it today. Okay.
Ma'am, you have tutorial class also of both the sections today.
Not today, tomorrow.
Oh, today's Tuesday, right?
Yeah. So if tomorrow morning, if you are free, then I can take the class tomorrow morning also. 10 to 10:50 your scheduled class is there, and before that or just after that, if you have any time, then I can take. Okay, let in the evening class 4:30. It may be extended to 6 o'clock. What is the problem? There will be no issue. I will complete
no issue at all.
Okay, so if you want to read tomorrow yourself, then you can have the tomorrow free, and in the evening you will complete the course. ठीक होगा? इवनिंग को आज कंप्लीट कर देंगे.
Yes, ma'am.
Okay. ओके, सो इवनिंग में इफेक्टिवली हम लोग अगर 4:30 से अगर 6 o'clock ले जाएंगे ना तो कंप्लीट हो जाएगा. And tomorrow morning वाला अगर 10 to 10:50 if you want then I can take the class and I will solve some. अगर आज इवनिंग में सारा कॉन्सेप्ट खत्म हो जाएगा जेनोटाइड को and some न्यूमेरिकल भी अगर हम लोग कर लेते हैं तो मॉर्निंग वाला क्लास में those who want to join you can, otherwise you can read also. I will take the class if I will take the class then solve some numerical. So you can follow that.
Ma'am, take the morning class.
मॉर्निंग क्लास ले लेंगे हम, मॉर्निंग क्लास तो ले लेंगे कल. तो आफ्टरनून क्लास कल ट्यूटोरियल क्लास दोनों नहीं लेंगे, ठीक है. मॉर्निंग का क्लास ले लेंगे, आफ्टरनून तुम लोग खुद से पढ़ाई करो, 2 पीरियड मिल जाएगा तुम लोगों को पढ़ने के लिए. तो आज 4:30 वाला क्लास में मैक्सिमम जितना होगा हम कवर कर लेंगे. अगर कुछ बचा हुआ होगा, बचा हुआ मतलब कॉन्सेप्ट तो क्लियर हो कवर हो जाएगा, बस कल अगर न्यूमेरिकल पार्ट अगर बचा रहेगा कुछ सॉल्व करने का तो कल मॉर्निंग वाला क्लास में करेंगे, ठीक है. और जब अगर पॉसिबल होगा तो हम न्यूमेरिकल बहुत सारा लिख के तुम लोगों को पोस्ट कर देंगे अभी, ठीक है. आज पोस्ट कर देंगे तो कल तक तुम लोग सॉल्व कर लोगे. Okay, so let's stop this class and from this filter part and rectifier part, if you are getting the time, just this period is no class you are having, so you can do it yourself. Okay, I'm just uploading that concept. You go through the concept and solve some numerical. You all have the book with you?
No, ma'am.
Not having the book. So
no, ma'am, are you talking about boiled state?
Any book if you are, whatever the book you are following, it may be Boylston or it may be your Millman Halkes, or it can be other book also like J.B. Gupta book is also there also it is nicely written and lots of examples are given. So any book if you are having then you can go through it.
Ma'am, can you repeat the names again?
Boylston is one book. Okay, Robert L. Boylston is their author name, Electronic Device and Circuit. And one more is Millman Halkes. Actually Millman Halkes थोड़ा सा टफ होता है, बहुत ब्रीफली दिया रहता है and इतना सारा एग्जाम्पल्स नहीं रहेगा उसमें. And one more book is J.B. Gupta is also there. J.B. Gupta, one Indian book is there, but it is a very nice book. There also lots of examples are given. Numeric solved examples are given, so you can go through that book also. Okay, so just now I am
PDF of these books, ma'am, like J.B. Gupta or Wall Street, ma'am.
No. Actually, I think Boylston book is online available. You can go through the Boylston book online. It is available. Actually, officially in team platform, I cannot upload the PDF version of that book. That is a copyright issue is there. So you can go through it online. It is available. Boylston.
Share it on WhatsApp.
ऑनलाइन में अवेलेबल है. बॉयल्स्टर का कॉपी तुम लोग ढूंढ लो, PDF फ्रीली अवेलेबल रहता है, ठीक है. एंड एक काम कर रही हूँ मैं अभी, तुम लोगों को कुछ सॉल्व्ड न्यूमेरिकल भी अपलोड कर दे रही हूँ, ठीक है. तो तुम लोग उसको सॉल्व कर लो सो दैट इट विल बी बेटर. टाइम भी तुम लोग का यूटिलाइज हो जाएगा एंड यू कैन हैव द आइडिया ऑल्सो. Okay, so I'm just uploading the files. You go through it.
And that's Robert L. Boylston.